My name is Eric Swepston, and I will be doing the project video for EPRI-VAC. This is the conceptual design for vacuum boxes for fuel pool liner inspection. Our team members are Hussein Al-Mutawa, Jonathan Broom, Jeffrey De La Rosa Garcia, Daniel Farrell, Christopher Hankins, Austin Radford, myself, Eric Swepston, who is the project lead, along with Logan Williams. Our faculty mentor is Professor John Nettles, and our project sponsor is EPRI, Electronic Power Research Institute. We're working with their nuclear research sector. This is our poster for Senior Design 2 in spring of 2020. First we have our description, followed by the ROV, the controls, localization, electronics and power, followed by the vacuum box, which is the most important part. We will start with the description. Our main task was to develop two conceptual designs of an ROV to inspect weld integrity of nuclear spent fuel pools via a vacuum box. First, some background on nuclear spent fuel pools. Nuclear reactors work with fuel rods. Nuclear fuel has a half-life, as does all nuclear material. Thus, as time goes on, the nuclear fuel becomes less effective and needs to be removed and replaced with fresh fuel. This old fuel is put into fuel holding pools, pictured here. However, these rods are still radioactive and produce a good amount of heat. Thus, these pools are irradiated and high temperature. Our design must withstand the radiation and temperature of these pools. It must also inspect the flat areas of the walls, specifically these welds here along the edges, along with the welds in the corners. The vacuum box must be capable of applying positive 20 and negative 10 psi. The ideal dimensions are 20 inches in length, 6 inches in width, and 6 inches in height. The ROV is capable of maneuvering in X, Y, and Z axes. Additionally, the ROV will be equipped with a camera and LED lights to provide visual aid to the inspector. Next, we'll talk about the ROV itself. There are two designs for this section, for this fuel pool inspector. One design is for the upper section of the pool, and one design is for the lower section of the pool. The upper section of the pool is not as irradiated as the lower section, thus does not need to be radiation hardened at all, as there's very little radiation there. The lower section is highly radiated and does need to be radiation hardened, thus the two designs. This will be controlled via a tether, and that will house all of the pressure hoses, camera, power, and signal wires. There are different components of this design. First, we have the 3D printed ABS frame. Second is the vacuum box. Third are the vacuum pumps, the 3 red units shown here. Fourth are the latches, which hold the vacuum box to the frame. Fifth are the motors. There are 6 motors, 2 in each axis, to ensure ease of movement. Next, we have the pressure sensors, which are these cylindrical objects. Seventh is the LiDAR, which performs localization for our design. And eighth are the camera and LEDs, which are not visible. Next, we'll talk about the controls. Robot Operating System, also known as ROS, is a flexible framework for writing robot software. ROS ties all components together to work uniformly in the system. It simplifies the complexity of low-level devices and reduces the microcontroller programming, which is used to control multiple things. ROS implements a simple command via graphical user interface and will perform the desired actions provided. Future improvement is available with constant updates and third-party developers. These developers are typically hired by manufacturers to support their products so that people will use their products. This is a GUI design that our team came up with for the ROV. The main point of interest here is the 3D point map generated by the LiDAR. We also have controls set up here, along with some waveform outputs. These are the motors themselves. All of this can be changed and reconfigured, but it's a potential design. Next, we'll talk about the localization of electronics and power. For localization, we're going to be using the Ouster OS0 ultra-wide LiDAR sensor. We decided to go with the LiDAR sensor based on several things. We need to find an approximate location within the pool to mark any potential areas of interest when inspecting. Water interferes with most forms of sensors except for LiDAR, sonar, and ultrasonic. But due to crosstalk, LiDAR is preferred. The model that we chose has a built-in inertial measurement system, and that will be used for calculating movement on the ROV. ROS also has a physics simulation which aids in movement. It will calculate the distance required to move with respect to the IMU, and this will relay the information to the software. Next, we have the electronics power. All the power will be supplied from the surface via the tether. Shielded cables will be used for power and signal to and from the ROV to ensure signal integrity. Both DC and AC power are needed. The DC power is needed for motors, LiDAR, and camera, while AC power is used for solenoid valves, which are controlled via relays. The pressure sensor needs amplification via hardened transistors, as its output is about 3 millivolts, which is far too small to reach the surface on its own. Thus, it needs to be amplified to be sent to the surface and then stepped down to a readable level so that we can process the signal. Lastly, we have the vacuum box itself, which is the heart of the project. Pictured here is the vacuum box on the left. Again, you have the 3 vacuum pumps, the 3 pressure sensors, along with the latches. One note is the 3 different sections of the box. And multiple vacuum boxes are also needed. This is just the flat one we have pictured here. There is one that is triangular in shape, which is used to inspect the corners. Separate chambers, as shown here, aid in sealing to the wall during application of positive pressure by allowing sequential testing. We'll talk about that with the pumping procedure. The pumps used are a Venturi-style vacuum pump, and they utilize pressurized air to draw a vacuum. This is a major challenge that our team faced. How do you create a vacuum when you're underwater at 15 meters of depth? The pressurized air will also be used to help expel water from each of the sections. This pressurized air is provided from the surface via air hoses. Solenoid valves control where the air will go within each box, either to the vacuum pump or to the box itself. The box will be made from 304 stainless steel and hardened glass, along with a radiation-resistant gasket material. The pumping procedure is an interesting point. First, the ROV positions the box over the desired inspection area. Then it revs up its motors to push the vacuum box against the wall. Then compressed air comes into the box to expel the water from that area via the check valve. Once it's sufficiently expelled, the vacuum pump then engages. This sucks out the air that's in there and creates a vacuum, thus sealing the box to the wall. Once this is done, the other 2 sections can be vacuumed out in a similar manner. Then, if any of these sections should be pressurized, the 2 remaining sections will hold that 3rd section to the wall. This simplifies a lot of challenges in holding the vacuum box to the wall while positive pressure is being applied. Due to the surface area, positive pressure would definitely push the box away from the wall. This concludes the video for EPRI-VAC